Hello everyone, I welcome you all again to the lectures of electromagnetic induction. This is 4th lecture part 3. I am Sameer Lavankar. So, let us begin. So, a brief outline of what we studied. We started with electromagnetic induction's definition in introduction part, followed by experiments of Faraday and Henry. There were 3 experiments, 1, 2 and 3. One involved coil in a bar magnet, second involved 2 coils, third involves 2 coils with a tapping key K. Next is phi b value, which is phi b is equal to B dot A. Faraday's law of induction, which involves epsilon value, which is equal to minus n d phi b by dt. Then Lenz's law and conservation of energy, then followed by motion electromotive force. For a conductor it was equal to B L V. Then we talked about eddy currents, applications of eddy currents and so on. Today we will start with inductance. So, now what is inductance? Let me iterate to you everything. It is a new concept, please be clear and please listen it carefully. So, let me go line by line. So, an electric current can be induced in a coil by flux change produced by another coil in its vicinity or flux change produced by the same coil. So, it is very important line here, please I will explain it to you again. So, electric current is induced. So, electric current I can be induced either to 2 parts, either in 2 ways. One is by another coil. So, there is a change in flux. A change in flux can be either due to different coil or it can be due to self coil also. This is a very strange thing, that how can a self inductor, how can a single coil or the similar coil or the same coil we are talking about can induce the current in itself. This is a new concept, it is a peculiar concept, we will talk about this also. So, same coil. An electric current can be induced in a coil by flux change. Flux change is nothing but delta phi p produced by another coil, either it can be another coil first thing in its vicinity, or flux change produced by same coil is second thing. However, in both the cases we will talk about it, we will talk complete concept of inductance is only and only due to these 2 parts. One is self inductance, one is mutual inductance. This is the only concept we need to deal here. So, please do not get hesitated as to why this another coil and same coil thing is happening. You will get to know everything in the subsequent slides. For now, let me move into second point. However, in both the cases the flux through a coil is proportional to the current, that is phi b is proportional to I. So, it was found that the magnetic flux phi b is directly proportional to I. Further, if the geometry of the coil does not vary with time, that is the area does not vary, area does not vary. If the area does not vary, then what happens is d phi b by dt. So, just d phi b by dt, di by dt, dt concept is being added here. So, d phi b by dt is directly proportional to di by dt. For a closely wound coil of n turns, the same magnetic flux is linked with all the turns. When the magnetic flux phi b through the coil changes, each turn contributes to the induced EMF. So, here as you can see on the right side also, that due to every turn there will be an induced magnet, there will be a change, there will be a part of magnetic flux being involved due to these n turns. So, there will be an n times d phi b by dt total flux. So, this concept is being only told in this last line, that due to this wounding of coils by n turns, there will be a increase, or there will be more and more magnetic flux going through the coil. So, moving on, therefore, a term called flux linkage. So, please understand or remember this concept, that there is a term called flux linkage. Why I am pressurizing on this situation is because flux linkage is being used in many example problems also and many concepts also in future slides. So, that is why please understand there is a term called as flux linkage. Therefore, a term called flux linkage is used which is equal to n phi b. This is nothing but n times phi. This is nothing but n times phi b for a closely wound coil, and in such a case n phi b is directly proportional to I. So, as in the previous slide it was given that phi b is directly proportional to I. So, for the total flux linkage we will directly write that n phi b is directly proportional to I. Moving on, the constant of proportionality in this relation is called inductance. So, this concept is nothing but inductance. This is inductance. We say induced current, what is this induce? It is nothing but a physics concept which is known as inductance. So, now this is the complete concept of inductance. This is now we will consider everything in this inductance part, this L part. This L is known as inductance. So, when will we convert this proportionality into equality, we get this into I. So, moving on, we shall see that inductance depends only on the geometry of the coil and intrinsic material properties. So, L is a function of geometry and intrinsic material properties. So, inductance depends only on the geometry of the coil and intrinsic material properties. Inductance is scalar quantity. Please make sure that this is understood very carefully, that it is a scalar quantity. Inductance is not a vector quantity. Inductance is not a vector quantity, it is a scalar quantity. Many times this confusion happens, that because you are dealing with vectors and scalars much more, because that is why. Please remember this, that inductance is a scalar quantity, it is not a vector quantity, it does not have any direction, it only has a magnitude. So, dimensions is mL2 t to the power minus 2 a to the power minus 2 given by the dimensions of flux divided by the dimensions of current. So, it is nothing but phi b by I, given by the dimensions of flux divided by the dimensions of current. So, it is flux here, this is current here. Next is SI unit. So, SI unit of inductance is Henry. The name Henry is devoted to the scientist Joseph Henry. We talked about him in the first lecture also. He was a very prominent scientist for electromagnetic induction. So, the SI unit of inductance is Henry and is denoted by capital H. It is named in honor of Joseph Henry, who discovered electromagnetic induction in USA independently of Faraday in England. So, see, just the strange concept of physics is both of them, even Joseph Henry and Michael Faraday, were doing research on similar concepts, not knowing anything about each other, and both got to know the same experiment. They got to know, they did the same types of experiments, they tried to evolve why is it happening for the same things, and even they do not know each other. It was later found that both were doing experiments on their different eras, different areas. Moving on. So, so as the inductance is being done here, you know what is inductance here, you know the properties, you know what it's a function of, you know the SI unit, you know the denotation. So, let us move on to two different. So, inductance is basically to two things. In the first slide also we learned that it is that the induction of current is done due to either another coil or by the same coil. So, this is only told as inductance is of two types, one is self inductance, one is mutual inductance. So, let us understand these concepts now, that is mutual and self inductance. So, let us first start with mutual inductance. So, what is the concept of mutual inductance? What is this mutual inductance? So, overall in rough area what we know from the concept of inductance is that anything, if the current is induced by another coil, then it is a concept of mutual inductance involved. So, let me iterate to you again line by line here. So, consider the figure which shows two long coaxial solenoids each of length L. This is the figure being talked here. So, two long. So, this is the first solenoid, this is the second solenoid, this is the first solenoid, this is the second solenoid. One solenoid is above the other. Coaxial means both have the same axis. If the axis is same, coaxial means same axis. Solenoid is known to you, anything which is coiled is a solenoid, and each of this has a length L. So, this was the first line. Moving on, we denote the radius of the inner solenoid S1 by R1. So, this is R1 and the number of turns per unit length by N1. So, N1 is nothing but if the number of turns is capital N1, then this is capital N1 per unit length, which is L. So, this is nothing but N1 value, small n1 value. Moving on, the corresponding quantities for the outer solenoid S2 are R2 and N2 respectively. So, this value is R2 here, and similarly N2 is equal to, if the number of turns of bigger solenoid is N2, then it is capital N2 divided by L. So, this is the second point, and this is the third point here. Moving on, let capital N1 and capital N2 be the total number of turns of coils S1 and S2 respectively, as being also used here. Now, please listen carefully from the next point, that when a current I2 is set up through S2, S2 is the second solenoid, S2 is the solenoid which is having a larger radius. So, when a current I2 is set up through S2, it in turn sets up a magnetic flux through S1. So, because of the change in current in S2, because there was a current being involved in solenoid S2, so there is a change in magnetic field. Now, is a magnetic field acting? Where is this magnetic field acting? It is acting on S1. It is going through S1. It is going through solenoid S1. So, let us denote this by F phi 1. Phi 1 is magnetic flux. So, the corresponding flux linkage, as I already told you, flux linkage concept will come again and again. What is flux linkage? I will go again and tell you. Flux linkage is nothing but N phi 1, N phi B value. N phi B value is nothing but flux linkage. So, corresponding flux linkage with solenoid S1 is N phi 1 is equal to M12 I2. So, what is this value? This is nothing but, again iterate, go back. So, what we understood from the concept of inductance is that flux linkage is equal to inductance into current. So, now in that forward slide it is given that N phi is equal to M I. Only this is the concept which is just talked here. So, I will write this line there. So, it is nothing but N phi into M I. So, as it is shown that current I2 is set up, that is why I2 is set up. Then where is the magnetic flux passing through? Where due to the current in S2, there is a magnetic flux talked about here is in S1, because it is mutual. We are talking about mutual inductance here. That is why anything passing through S2 has to be dealt in S1. So, therefore, we will talk about phi 1 value, hence phi 1. Because it is phi 1, we will talk about flux linkage of solenoid S1 only. Therefore, the number of turns of solenoid S1 has to be taken into picture only, hence it will be N1 here. Now, M is nothing but inductance. So, now this is just a denotion that M12 is called, please be very clear here, that M12 is called the mutual inductance of solenoid S1 with respect to solenoid S2. So, to denote this we write M12. So, I clearly explained you everything step by step, how this formula came, why there is a denotion by 1 and 1 here and 1 2 here and 2 here. Everything has been dealt very clearly. So, hence we got a new formula that the corresponding flux linkage with solenoid S1, please be sure it is solenoid S1, is N1 phi 1 is equal to M12 I2. So, M12 is called the mutual inductance of solenoid S1 with respect to solenoid S2. It is also referred to as coefficient of mutual inductance. So, either we will call it as mutual inductance or we will call it as coefficient of mutual inductance, mutual induction. Moving on. So, now for these simple coaxial solenoids, coaxial is nothing but having same axis. For these simple coaxial solenoids, it is possible to calculate M12. What is M12? We have already used here. This is M12. The magnetic field due to the current I2, the magnetic field due to the current I2 in S2 is mu naught N2 I2. The resulting flux linkage with coil S1 is. So, now we already know what is flux linkage. It is equal to N phi, because we are talking about the flux linkage of solenoid S1. So, therefore, this flux linkage will be N1 phi 1. Now, from this concept here we know N1 is equal to capital N1 by L. Therefore, capital N1 is equal to N1 into small l. We will just write here capital N1 is equal to capital N1 into small l into magnetic field is nothing but mu naught N2 I2. Therefore, N1 phi 1 is equal to N1 L into mu naught N2 I2 into area. As we already know what is phi value is nothing but B dot A. This is the value of B. Area is nothing but pi. That the solenoid we are talking about is S1. So, the area will be involved will be of S1 only, hence it will be pi r1 square. Therefore, it is pi r1 square. Reiterating the terms, we will get it as mu naught N1 N2 pi r1 square L I2. This is nothing but the flux linkage. Please understand this concept again and again. Please remember this is flux linkage. So, this is nothing but N1 phi 1 is equal to mu naught N1 N2 pi r1 square into L into I2, because it is a mutual inductance. So, in solenoid S1 where will be the current acting? Current will be acting in solenoid S2. So, anything which is acting in S2 will be denoted by I2 here. Current acting on in solenoid S2 will be denoted by I2, where N1L is the total number of turns in solenoid S1, as I wrote here also. This is the thing told in the next point there, where N1L is the total number of turns in solenoid S1. Thus, M12 is equal to mu naught N1 N2 pi r1 square L. From where did this thing come? We know N1 phi 1 is equal to M12 I2. So, just equating this, therefore, I2 gets cancelled, and therefore, we get M12 is equal to mu naught N1 N2 pi r1 square L. Hence, we got the value of mutual inductance. Moving on. Note that we neglected the edge effects and considered the magnetic field mu naught N2 I2 to be uniform throughout the length, that is B value is constant. Note that we neglected the edge effects and considered the magnetic field mu naught N2 I2 to be uniform throughout the length and width of the solenoid S2. Where is S2 acting? This is S2. So, magnetic field is intact, in this position, in this complete position magnetic field is intact. This is only the line being dealt there. Next, this is a good approximation keeping in mind the solenoid is long, implying length is very much greater than R2. So, length here for this is very much greater than R2. So, finally, this was the first concept of mutual inductance. What we learned today was flux linkage is a very important term. What is flux linkage? Is nothing but N into phi. What is N? N is number of turns. What is phi? Phi is the magnetic flux going through that area. Here that area can be a solenoid. So, N phi is directly proportional to I, and N phi is equal to remove the proportionality, we write N phi B is equal to L into I. L is inductance here, which is a function of geometry and intrinsic material properties. The SI unit of inductance is Henry and is denoted by H. So, today we learnt what is inductance and what is a little bit about what is mutual inductance. We derived the formula of mutual inductance for solenoid S1, for solenoid for solenoid S1 due to a current produced in solenoid S2. Hence, after this mutual inductance formula, I conclude this lecture today, and thank you.